Hello, AP Calculus. We are back to conclude 3.2. So, here are my 3 goals. I want to just reiterate what's going on with that whole power rule shortcut. Talk about differentiability as it pertains to graphing. How can we look at a graph and say, that's not differentiable or that is differentiable? And then how can we talk about differentiability from a context of computing with algebra using limits and the definition of the derivative? So let's get to it. If you recall, power rule was if a function can be written as, say, x to the nth power. We started out with just talking integers for n, but then we expanded it to be any real number. The derivative of x to the n can be obtained if you bring the n down as now the coefficient and then take 1 away from the exponent. So this makes the need for the definition of the derivative less necessary. Calculations now should be much easier. So how does this work out? Well, if you look at a couple of the odds from page 108, three to the x power, ooh, that's a good one. We get second derivatives too. Anyway, let's just do those first 2. The idea is, if I can just say the 3 doesn't exist for now, what's the derivative of x to the 6? You can actually bring the 3 out and multiply it by the derivative of x to the 6. So just treat the 3 as if I can multiply constants times that 3. So the 6 comes down, and it's going to be 3 times 6, which is 18, and then it's just going to be x to the 6 minus 5 power, x 6 minus 1. That's it. That's all you got to do for power rule. For this second one, you have to rewrite it as a fractional power. You can't just leave it as a root. So exponent divided by root is how you would change that root into a fractional exponent. So we got to do that move first. You got to call that 9x to the 2/3 power. Then I can bring the 2/3 down, multiply that by 9. So it'd be 9 times 2/3 times x to the 2/3 minus 1. So 2/3 of 9 is 6. 2/3 minus 1 is going to be negative 1/3. And then just keep in mind that we can rewrite this as a positive exponent by moving it to the bottom part of the fraction. Now the fraction isn't really present right now, but you can create the fraction by simply placing the x to the 1/3 on the bottom. Like that. And keep in mind that that's the same thing as 6 divided by the cube root of x. So we constantly have this, it's almost like speaking 2 different languages. If it's a root, I know what it is as an exponent and vice versa. So all 3 of these are the same derivative. Now, if you look at some of these, they talked about the second derivative and even the third derivative. So I'm gonna work through a couple of those examples as well, just to get us, just getting us practicing with multiple derivatives. For instance, number 17, it says if z is equal to 25t to the 9/5. What does, and then they use the notation, the derivative of z with respect to t squared, that just means take the second derivative. So take the derivative twice. You can write the notation as z prime if you're taking the derivative of both sides. So z prime would be the same thing, bring the 9/5 down, multiply 9/5 times 25. And then take one away from 9/5. So there's some cross-canceling action. This turns into 45. And this turns into t to the 4/5 power. So d squared z with a little t subscript right here is just the same as z prime. These two are the same exact thing. Bring the 4/5 down and multiply. And subtract 1 from 4/5. So you're going to get 36t to the negative 1/5 power. Yeah. And let's just get in a habit of writing with positive exponents as much as we can at the very end with the final answer. So I'm going to replace it with this notation because here's the thing. If they ask for that, you should probably give them that at the end as a part of your final answer. I think that'll do for this part. Let's talk differentiability with graphing. We went over this in class a few days ago. We talked about how asymptotes were trouble. We talked about how holes in the graph were trouble. Oh no, the holes in the graph weren't necessarily trouble, it was the jumps. We talked about vertical tangent lines. And how they happened at little things called cusps. They look kind of like this. We talked about a lot of times absolute value functions would create difficulties. Because they abruptly shift from one part to another. They abruptly shift from, hey, you are able to, hold on, what am I trying to say? From the left and from the right, those limits didn't match up. And a derivative is, in essence, a limit. So when the limit from the left doesn't match with the limit from the right, and you have sharp turns, that means that the slopes of the tangent lines are different. Okay, so I'm saying too much here. Let's talk about the graphs themselves. So there's a few other ones like this, but let's just check out what we got going on in the textbook to help us through this. So I'm looking at number 31 right now. So my first question to you guys is, do you see a place where this function is not differentiable? right away you should be thinking at x equals 2, this function is not differentiable because it's got a cusp right there, which is going to create a vertical tangent line. But you know what? Let's make sure we're following directions on this because I want to answer the question they're asking. All right, so they're saying, what's the value of f prime of -1, f prime of 1, f prime of 2, and f prime of 3? And they're just saying estimate things. So remember, f prime is the slope of the tangent line at a specific spot. You might want to write that down somewhere. F prime is the slope of the tangent line at a specific x value. So right away, we talked about how f prime has issues right here. You would say f prime of 2 is non-differentiable. So we could kind of say that the derivative doesn't have a defined value there. So f prime of 2 is undefined. Hopefully you guys can see that on here. Kinda. It's undefined. The rest of this task is just making sure that you guys can do estimates for tangent lines that cross at specific spots on the graph. So -1 corresponds to about right here. Okay, so the question is, if we were to draw a line that only crosses at that one spot, what would you say an estimate would be for that line? What would its slope be? Well, it looks like it's about -1, 2, and it almost goes through 0, 1. I'm sorry, it almost goes through 0, 3. So it looks like it rises 1 unit and runs 1 unit. So the slope of this tangent line at -1 appears to just be 1 over 1. At 1, it kind of looks like we've reached a peak at some point. We've reached a max value. And if we've reached a max value, that means that all the slopes of the tangent lines were starting to get less steep, less steep, less steep, and then they basically just completely leveled out right here. So what would the slope of that line be? It rises 0 and runs whatever number you want it to be. 5. Why not? Up 0 over 5. All right, so the slope of that line, the derivative at 1 is 0. We've already talked about 2. 3 goes to the point 3, 0. And it does one of these deals. So again, it looks like it's just a mirror image of what we had up here. It almost appears like it's going through the point 2, 1. So if you went down 1, right 1, you're pretty much talking about the rate at which that line changes. So -1 over 1 means that the slope of that tangent line is -1. So they don't really talk too much further about differentiability other than just recognizing that sharp turns create points of non-differentiability. So that, I think we can at least put to rest number 3 for now, or number 2 for now. And the last one, the definition of differentiability on a closed interval, okay? The definition of differentiability that's going to help us work our way through, something like, 23, is basically saying that the limit as h approaches 0 from the left of f of x plus h minus f of x over h, that limit must equal the one from the right in order for differentiability to hold. And if it's on a closed interval from A to B, then from the left of A, and from the right of B, I want to make sure I got this right. No, it's the reverse. From the left of, that makes sense. Okay. So just think about a semicircle as a function. I think that's a really easy one to visualize. This is from A to B. So from the right of A, you have to have a limit here. And from the left of B, you also have to have a limit. So that's kind of how you're working your way through those definitions to see if it's differentiable in a closed interval. Yeah, so let me do 23. I think I'm going to end it there and explain whatever else I need to in class. So, yeah. 20. You know what? Let's do 21. Let's determine if f is differentiable on the two closed intervals with 1 over x. And I'm going to turn this off so I got some actual room to work. F of x equals 1 over x. So the first one I'm testing is it differentiable from the interval 0 to 2? So what you're asking is, does the limit as x or h approaches 0 from the left of this function when I plug in my right endpoint, 2? So f of 2x plus h minus f of 2 over h. Does that equal the limit as h approaches 0 from the right of my left endpoint value, f of 0 plus h minus f of 0 over h? If it is, then we know that it's differentiable on that closed interval. So what do? Well, we plug in 2 plus h for my x, plug in 2 for the x, divide by h. So I can do two things at once. I can find a common denominator between these two values. So I'm just going to make it a 2 and make this a 2 plus h. And at the same time, I'm going to move this up and say instead of dividing by h, I'm going to times it by 1 over h. Instead of dividing by h, multiply by 1 over h. So you're left with the limit as h approaches 0 from the left of 2 minus, distribute the minus 1, 2 minus 1h, all over 2 times 2 plus h, common denominators, and then we multiplied by 1 over h, okay? So we kind of said, don't divide by h, multiply by 1 over h. So it's sort of like the h got absorbed into the denominator here. All right, 2 minus 2 is 0. H divided by h is 1. We have successfully canceled out the derivative. We've successfully canceled out the domain issue, which means we can plug a 0 in right there. It's going to be negative 1 over 2 times 2 plus 0. It's going to be negative 1/4 from the left. From the right, it's got to equal negative. Actually, I think they just both have to exist. They don't have to equal one another. Let's double check on that. Yeah, both limits just have to exist. So what I want you guys to do is change your notes here. I'm so sorry. We're 20 minutes in the video though, right? Those two limits just must exist. They don't have to equal each other. I'm sorry. My goal is not to create more confusion. My goal is to turn this chaos into logic. All right. Last thing. Let's just confirm this thing, and then we'll shut it down. Confirm that the limit exists from the right of 0. So we confirmed it here on the left. I'm going to erase that. Check. On the right, plug in 0 plus h here. Plug in 0. Oh. Can't do it. What is 0 from the left of an asymptote? Or 0 from the right of an asymptote? Looks like it's got an infinite value. So now what we normally would do is try to cancel out the h domain issue. But right away, I can't even compute f of 0 inside here. So what you'd say is, it is not, the limit does not exist from the right. So it's not differentiable over the interval. Okay. We'll talk more later. Thanks for watching.